Alright, let me tell you about something that's going to blow your mind. Imagine a world where quantum computers don't need to be cooled to near absolute zero, where they just work, right here, at room temperature. Sounds like science fiction, but LSU physicists are making it a reality. And the kicker? They used gold. Yep, gold. But not just any gold, engineered into something so precise it's like a quantum crystal made by humans, not nature. Let me break this down for you. Quantum materials are the holy grail of modern tech. They could revolutionize everything from ultra-fast computing to unhackable communication. But here's the catch: most of them require temperatures colder than outer space. Why? Because heat makes atoms vibrate, and those vibrations mess up the delicate quantum states we are trying to harness. Think of it like trying to dance a perfect waltz while someone's shaking the floor beneath you. Not happening. So labs are full of these massive, expensive cryogenic machines. But what if we could skip the chill? That's exactly what this team did. Now, here's where it gets wild. Instead of hunting for a rare material in nature, these researchers built their own quantum crystal from scratch. They took a thin layer of gold and carved it with nano-scale precision, creating these artificial meta-atoms that act like a lattice. It's like designing a musical instrument that plays notes no natural material ever could. And this thing? It can sort different quantum states of light at room temperature. No cooling required. That's not just a technical achievement, it's a paradigm shift. Imagine quantum computers that fit in your pocket instead of being buried in a lab with a fridge the size of a car. Let me unpack this. Light isn't just light. Sunlight, lasers, and even your phone's screen emit photons, but those photons behave differently at the quantum level. Until now, telling them apart needed supercold detectors and millions of measurements. This metacrystal. It does it on its own, like a quantum traffic cop directing photons along specific paths. And here's the kicker: it preserves their quantum coherence, which is like the soul of quantum information. Without coherence, quantum states collapse, so this material is basically a shield against the chaos of the real world. That's why I think this could be the missing piece for practical quantum tech. No more fragile, cryo-dependent systems. Just robust, scalable solutions. But wait, there's more. This isn't just one material, it's a blueprint. The team calls it a quantum statistical plasmonic metacrystal, and it opens up a whole new class of materials. Think of it like the periodic table of quantum engineering. Instead of relying on luck to find a rare substance, scientists can now design materials with specific quantum behaviors. That's a game changer. It's like moving from alchemy to chemistry, finally having the tools to build what you need, not just hope to find it. And here's where it gets even cooler. This tech could turbocharge solar panels. Right now, solar cells waste a ton of energy as heat because light gets trapped. But this metacrystal could guide photons more efficiently, turning more sunlight into electricity. If that works, we are talking about a leap in renewable energy that's directly tied to quantum physics. That's the kind of cross-pollination between fields that leads to breakthroughs. It's not just about quantum computing anymore, it's about reshaping energy, communication, and computation all at once. So what does this mean for the future? Well, personally, I think we are looking at a future where quantum tech isn't confined to labs. It's going to be everywhere: smarter devices, faster networks, cleaner energy. But there's a catch. This is still early-stage research. Scaling it up, manufacturing it affordably, and integrating it into existing systems. That's the real challenge. But if this team's work proves scalable, we are talking about a technological revolution. And honestly, I can't wait to see what comes next.